Hello everyone. My name is Pratik Falle, and I'm currently pursuing my bachelor's in computer engineering at Vidyalankar Institute of Technology, Mumbai. Today I'll be presenting a PPT on fault diagnosis of rolling element bearing using artificial neural network. Starting from the predictive maintenance in an industry, maintenance is the most essential part which keeps machine in working condition and avoids the failures. This improves machine's life and increases production efficiency. Basically, there are three types of maintenance. First is the reactive maintenance. This is the traditional approach in which when the part or component fails, then only it was to be replaced with lead to machine downtime and unnecessary inventory cost, that is spare parts cost. In preventive maintenance, the main focus is on periodic maintenance. The scheduling is done beforehand. So after specific interval of time, replace certain part whether it is in good condition or bad condition. Nowadays, predictive maintenance is used where the condition of machinery is monitored in running condition. Faults are predicted. So as shown in the slide, predictive maintenance has following characteristics or techniques. So moving on, today the world is connected through internet. Because of internet, people can work from anywhere during the pandemic situation. The best example is this conference. Therefore, therefore, predictive maintenance, when connected to AI and IoT, artificial intelligence, and Internet of Things, gives remote operating facility and automatically gives prediction related to condition of the machinery and remaining useful life. So here are some predictive maintenance techniques, out of which most commonly used technique, as we can see from the chart given, is the vibration analysis. The main advantage of vibration analysis is each fault develops its unique vibration signature with respect to the operating frequency or the running speed of the shaft. So in as we can see, conditioning monitoring. So condition monitoring is the major component of predictive maintenance. In condition monitoring, we monitor some parameters of the machine such as vibration, temperature, etc. to identify a significant change which indicates a developing fault. So following are the advantages and disadvantages of condition monitoring. So advantages are extended machine life. Of course, the machine life becomes a little more, or possibly more than we actually get. So second is to safely extend overhaul intervals, improve product quality, of course, enhance product safety. Disadvantages are equipment costs are increased, of course, and so are already a lot. Operation costs are there. Skilled people are required for the job. Strong management commitment is always needed. So the motivation. Conditional monitoring has emerged as an important technique in manufacturing industry for predictive maintenance and online monitoring of process and equipment. So bearing is the heart of every machine that we can see today, as bearing has a lot of applications too. They are used in IC engines, centrifugal pumps, turbine shafts, crank shafts, etc. This enables the machine to withstand shock loads and other types of sudden loads. So aim of the research is to simulate fault in rolling element bearing and perform vibration analysis to avoid catastrophic failure. So we have the bearing, we take the bearing which has faults, we use the sensors to get the data from the bearing, and then We use the amplifier for this data to be able to read properly. So in data acquisition is where the data is actually analyzed properly, sent to the advanced signal processing. And we see the research at we are using FTD graph. So various faults related to rolling element bearing and their unique vibration signatures. As we can see, there are three types common faults: fault at outer race, fault at inner race, fault of rolling element. So the dominant peak we can see is BPFO for outer race, BPFI for inner race, and BSF for rolling element. So this is the experimental setup. We actually use the fault at inner race and we use the bearing at the shafts. So this is the methodology that we have used. Here is the methodology of the research work. Acquired vibration spectrum for healthy and faulty system are used for faulty classification ANN, artificial neural network. So an experiment, the methodology is like an experimental fault simulator setup was used for the study. Vibration analysis of health system was carried out. The fault are developed at the inner rays of 0.25 mm and zero point 0.5 mm respectively, and the analysis was carried out. The vibration rate of healthy and faulty system was compared and validated with literature available. ANN was used to detect the fault automatically. So ANN. Nowadays, a rise of smart systems which are intelligent enough to make decisions. There are different machine learning techniques which help in decision making. ANN, an artificial neural network like humans, learn by examples. It's like human neural structure. It has got three layers: input layer, output layer, and a hidden layer. In the hidden layer, all the Boolean operations are performed. In this, each neuron holds a number called activation number. The activation number is 0 or 1. All the inputs are converted into binary function using sigmoid function or rectified linear unit. So ANN was developed in MATLAB, having four layers: one input, one output, and two hidden layers. The size of the input layer is 0, or is 10. Output layer is 3, that is 0, 1, or size of the hidden layer is 5. The activation function is hyperbolic tangent sigmoid function. The training algorithm used as gradient descent with propagation, as we can see. So calculation of ball pass frequency at inner race. Theoretically, the values of BPFI were calculated, which are as shown in table. So we have the RPM, we have the BPFI, and we have the formula used. So the results, we have the comparison of vibration spectrum for 0.5 mm defect of inner race of ball bearing at 10 Hz, 11.66 Hz, 13.33 Hz against amplitude. So figure shows the comparison of experimental result. The calculated values of BPFI and experimental values are varying slightly due to fluctuation in input speed. But the vibration spectra shows dominant peak at BPFI, which is as reported in the literature available. This figure shows the frequency spectrum of a healthy and defective system at 700 RPM, that is 11.66 Hz. It is clearly seen that for a healthy system, the dominant peak is seen at first multiple of operating frequency, that is 11.67 Hz. And for the defect, it is at BPFI along with two side bonds. As the severity of the defect increases, the amplitude of vibration increases, and the unique vibration spectrum is independent of shaft speed. So conclusion, the amplitude of BPFI of defective bearing is approximately higher than the amplitude of healthy bearing at BPFI. As the severity increases, vibration amplitude increases. The amplitude of BPFI is higher than the amplitude of healthy bearing at BPFI. ANN model was developed and tested which has accuracy of 94.27%. Total 50 samples were taken for each case. So for healthy system 150 data samples, for defective 150 into 2, that is 300. So 70% of the data was used for training purpose and 30% was used for testing purpose. Therefore, it can be concluded that integrating ANN with online condition monitoring will make a powerful tool for machine condition monitoring. And if connected to IoT, then real-time condition monitoring can be achieved without actual site visit. Thank you.